Right. I'll let you know as soon as I'll be thinking about it. Our test is next week, right? Yeah, y'all need to start preparing. Um, so we have several applications of the right-hand rule. The first application has to do with this formula, F equals QVB, sine theta. And I'll review them and then we'll look at some examples. And then you'll see some examples where they're combined. Like some of the problems you have combined right-hand rule things. So when F is equal to QVB, we let our fingers go in the direction of V. They fold towards B, or you can think of B as coming out of your palm. And then third, your thumb gives the direction of the force. And typically, it's fingers, palm, and then thumb. But if you're given your force, then you have to sort of go backwards at that. And so, for example, if I have V in this direction, and my magnetic field is in this direction, I would use my right hand. V, B is to the left, so it's like this, and then it's going to be out of the page. And so the force here is going to be like that. The second application of the right-hand rule is F equals ILB sine theta. Here, my fingers are in the direction of I, or L, however you want to think about it. My palm, or the fingers fold towards that, and then my thumb gives the direction of the force. So this is an identical application of the right-hand rule to the first one. These two are basically the same. It's just my charge is being constrained to the wire. And so for example, if I have a current in this direction, so this is I, and it sits in a magnetic field that say is like that, then I would let my fingers go in the direction of I. B is into the page, so my palm, like I don't know how my palm should be immediately, but since B is into the page, it's going to be like this. And so then the magnetic force, F, is going to be up. So F here is up. And then the third application of the right-hand rule has to do with this equation. B is equal to mu naught I over 2 pi r. And that has to do with the, is it 2 pi or 2r? It is 2 pi, right? That has to do with a long straight wire. And if I have a long straight wire that has a certain current in it, there is a magnetic field at a certain point. I'll call that point P over here to the side. And I can calculate the magnitude of that magnetic field. This is my distance, r. And then I can find the direction of the magnetic field by using my right-hand rule. Here, my thumb goes in the direction of I, and my fingers wrap for the direction of B. And so here, for example, I is up, and so my fingers go into the page on the right-hand side and out of the page on the left-hand side. So into the page on the right-hand side, out of the page on the left-hand side. You can see another iteration of that, or a couple different ways I could do that. Like you could also have your wire like that be I, and in that case, it's sort of the same. Into the page right here, out of the page like that. The other way that I could do it is you can have your wire either coming into or going out of the page. So for example, if I have a wire like that, and if this is my wire, that would mean that it's going into the page like that. And so I let my thumb go in the direction of the current, and then it wraps around to give the direction of the magnetic field. And in this case, I would draw my magnetic field as a clockwise circle. So my magnetic field would look like that. That would be B. And if I ask you for the direction of the magnetic field at any particular point, say at this point, the magnetic field is always going to be tangent to the circle. And we did some questions like that in class. So those are the three applications of the right-hand rule. There is I would call it, say, 3A. 3A, let's call it 3A. because it's really the same, and that is when you have a solenoid. We're going to see that tomorrow, but a solenoid is really just a coil of wire. We did see that last time. And when I have a coil of wire that has a current in it, so in this wire, there is a current that's flowing clockwise. When that is the case, it generates a magnetic field at the center, and we'll find an equation. I'll write it here in just a second. The magnetic field is in the center. It's all around, but particularly there's a magnetic field in the center. I let my fingers go in the direction of I at any point, all the way across. Let my fingers go in the direction of I, and then they show, my fingers wrap around to show the direction of the magnetic field. Fingers in the direction of I, into the page in the middle, out of the page on the outside of the circle. So into the page right there, and then out of the page, out of the page over there. Okay? And we can calculate that magnetic field is mu naught I over 2R. And remember, I told you the way to tell these two equations apart is often, or there is an N at the front of that, because usually in those coils you have many turns of wire when you have a solenoid switch. So those are sort of 3.5 applications of the right-hand rule. Yeah. So I let my thumb go in the direction of the current, just like we did up here. Thumb go in the direction of current at this little section of wire, and it goes into the page, out of the page. So just like what we did with 3, it's just, it's in a circle now instead of a long straight wire. Yeah, there's going to be, there's probably going to be 6 or 7 questions. That many? No. 4 or 5 questions that are right-hand rule. That's a quarter of your test. So that's a great opportunity for you, right? That you get all those right. Well, let's do some that are more difficult. And like, for example, number 9 here. I don't think that we've done one like this. Yeah, we've done one, something like this. So let's look at number 9. I have a positive particle. It approaches a current-carrying wire, and I want to know the direction of the current that causes the particle to travel the path as shown. I'm going to do one that's just a little bit different, because I think we've done this one. Let's say, instead of a positive particle, let's say that we have a negative particle. And then let's say that that particle is traveling along in this direction, and it follows a path that looks like that, because there is a wire right there with some current in it. And I want to know, what is that current? Like, what is the direction of that current? The answer is either up or down, right? Or there is no current. But we know that there has to be a current, because this particle has felt a force, and that force is causing the particle to move upwards. Oh, that's our custodian. Okay, so several things we have to recognize. I like to draw another vector diagram down here at the bottom. First, my velocity vector is in that direction. That's just because this particle is traveling in that direction initially. Now later it's not traveling that direction because the force pulls it up. And the force is in this direction. So that's our first thing. Our first step is to figure out what is the magnetic field. Thumb in the direction of the force, fingers in the direction of V. So my magnetic field is what direction? Into the page, right. So my magnetic field looks like that. So I know on this side of the wire, my magnetic field is like that. And then on this side of the wire, my magnetic field looks like that. Now, the second step, so this is the first step. The second step is to figure out what is the direction of the magnetic field. And I know that my magnetic field goes into the page here, and then it's going to have to fold underneath and then come out of the page. And so that tells me that my current in this wire has to be down. So my current is down. That would be the answer. Okay? Oh, yes. So I forgot. It's a negative particle, so it's not down. It's up. Because the magnetic field that causes this force, since it's a negative particle, the magnetic field is actually opposite what I found it to be. See, this is going to be hard for the test. Whenever you see negative or electron, you need to put a big old star right next to it, because you might forget, just like I did by the end of the problem, that you're dealing with a negative particle instead of a positive particle. So really, my magnetic field should not be into the page, but my magnetic field should be out of the page for a negative particle to give it that force. And then this changes. And so then my current is the opposite direction. But I could have just done it, treated it like a positive particle, and then just switched it. But you got to remember, don't be like me. Be like, and remember. Y'all can remember that, right? Put a big star if you see a negative particle. If it's negative or if it's an electron, make sure you put a big star next to it. I usually try to bold and italicize those words.
You know the force was up just because how like the particles.
Oh yeah, good question. Yeah, so I know that this thing is being pulled upwards like that. Yeah, this could be a good free response question, but I would include a calculation with it. And I'll tell you what that's going to be. I'll prepare you like I've done before. I'll try to have that by tomorrow so y'all can be getting ready. But it might be Monday before I have the free responses. I was telling, they were asking earlier, what are the free responses? And but I was saying that the free response are probably going to be easier than they were for the previous test, just because these questions are less involved. But I'll still do the same where I tell you what they're going to be. I want you to be prepared for those. It's a big chunk of the test. Okay? Okay? What's it?
The ones are pretty easy.
Which one?
The ones from the first test.
Yeah, well, if you know them, they're easy. If you don't know them, they're hard. Let's see. One that trips up people, we did one like this in class, is one like number 4. And let me just step through this. We'll do one that's slightly different. If I have, say, a magnetic field, let's say I have a magnetic field that is in this direction, and I have a proton that is moving through the magnetic field in that direction. So that's the velocity vector. And I want the proton to go straight through that magnetic field. Now I know the proton's not going to do that because there is a force acting on it. I can figure out the force. It's going to be into the page. So the force on the proton isn't that right? Yeah, into the page is the force on the proton. So the magnetic force on the proton, I'm going to call FB, is down. So normally this proton would follow a path that looked like that. It would pull it into a circular path. However, I can add another electric field, or add an electric field that will cause this proton to not be pulled down, but to pull it up. So I want to know then, what is the electric field that will cause a force to go up? And you need to remember, because you'll probably have a question like this on the test, that the force due to the electric field is in the same direction as the electric field. And that force, F, is equal to Q times E. Whereas this is FE. FB is equal to QVB. And so in this case, I need an electric field that is upwards in order to balance out that magnetic field. Is that right? Did I do that right? No, shoot. I'm sorry, guys. Can I fix it? Yeah. So my magnetic field, very, very sorry. My magnetic field is down. That's B. So my velocity is to the right. So my magnetic force is into the page. So FB, I'll do it in black, is into the page. So I want FE to be what direction? Out of the page. Yeah, I'm very sorry. So the electric field is also out of the page, or in the plus Z direction. All right. And in number 4, we actually had to calculate what that velocity is. In number 4 over here, it says an electron moves through a region. Can y'all read that? Let me zoom in a little bit. Is that better? So an electron moves through a region across electric and magnetic fields. The electric field is 2,000 volts per meter. So E is equal to 2,000 volts per meter, or newtons per coulomb, remember. And it's directed straight down. And the magnetic field is equal to 0.8 Tesla. And I want to know what is the velocity of the electron so that the electric force will exactly cancel the magnetic force. And in order for that to happen, FB has to equal to FE, in which case QVB is equal to QE. And in this case, the Q's cancel. It's not important. So I'm looking for the electric velocity. So I solve for V. It's equal to E divided by B. And that's going to equal to 2,000 over 0.8. I think it was 2,500. Okay? That would make a good free response question. Something like that. But not only would you have to calculate the velocity, but I'd ask you to find the direction of the electric field, or the magnetic field, or the velocity, or something similar to that. Yeah, let's plan on one of those, that being one of our free response questions. And the second one will be the RC circuits, where you're solving for the charge, the voltage, the current, or most likely the time, where you have to do the natural log of the exponential function. Most likely that will be it. Y'all can do that, right? Okay?
Like one of them would be like this, or we just figured out that the electric field was opposite of the force of the electric field was opposite the force of
The magnet.
magnetic.
Yeah,
Like
because you want it to go through undeflected. In fact, what they'll do is they'll take the electric field and the magnetic field, usually the electric field because it's easy to modulate, easy to change, and they'll change that, and that causes the beam of electrons or protons to move around. Remember the old TVs? Like before we got flat screens?
big ones.
The big ones, right. Yeah, so that used this idea where they shot out a stream of electrons to the back of the glass screen to create the different colors, and they had crossed electric and magnetic fields that would move those electrons around to the right part of the screen. Isn't that crazy? Yeah. Okay, let's see. Yeah, let's do that as a free response. That would be a good one.
Can we do a question like the RC?
Yeah, of course. Let's see, that's exam 3. I don't have many good ones. Can I just make up one? Yeah, so let's say we have a discharging circuit. And I might tell you it's discharge. Yeah, I'll probably tell you. Or I'd say that you have this charge capacitor that discharges over time. And so it looks like this. Let's say that this is 2 microfarads. Let's say that, you have a resistor here. Let's say that this is 5 mega ohms. And say this is 10 volts. So I want to know at what time is Q equal to, I don't know, 5 microcoulombs? That would be the question. I might also ask you, how long does it take to fully discharge this capacitor? You might be able to tell me that right away. Can you tell me what is the time that it would take to fully discharge this capacitor? No, you just don't remember. That's okay. Tau, the time constant, is equal to RC, which is equal to 5 mega ohms times 2 microfarads. So it's equal to 10 seconds. So the time to discharge is equal to what? Times 10, which 100, right? So it's equal to 100 seconds, 10 times the time constant. If you don't see that on the free response, you'll definitely see it in the multiple choice. So make sure you understand time constants and how that characterizes these exponential growth or decay functions. That it takes 10 time constants to fully charge or discharge. Now let's get back to this original question. So the first thing is I need to figure out what is the charging or discharging function look like. And if I go to my equation sheet, it tells me there. And I'm looking for Q discharging, so it's right here. The Q is equal to big Q times e to the minus t over RC. Big Q is equal to CV, e to the minus t over RC. So I can put in some numbers here. I have 5 microcoulombs is equal to C times V. That's 2 times 10 are 20 microcoulombs times e to the minus t over RC. I've already found RC. It's up here. So over 10 seconds. So that's 5 over 20. What's that? 1 over 4.25 equals e to the minus t over 10. And then 0.25, right, that's 5 over 20. And then I do the natural log of both sides. The natural log gets rid of that exponential. And the natural log of 0.25, make sure you know how to do it on your calculator. It's usually next to the EX button. I get negative 1.39 equals negative t divided by 10. So when I take the natural log of that exponential, that exponent comes down into the numerator. So that is equal to, if I solve that, t is equal to 13.9 seconds. And then I can just do a quick little check that I'm going to, if I were to plot out q divided by t, it would be a function that looks like this, because it's a decay function. That's what this exponential is. You will have to identify that on the test to identify the proper decay or growth functions for a charging or discharging capacitor. So q over t, I know that it reaches 0 out here at like 100 seconds. That's when it reaches 0. And I know that the maximum the maximum charge is 20 microcoulombs. And I'm looking for somewhere where it's at 5 microcoulombs. So that's going to be at about t equal to 14 seconds, or 13.9 seconds. Really, I'm just checking to make sure that this 13.9, it better be less than 100 seconds. Because if it's not, if it's more, then I made a mistake somewhere.
So you got 100 seconds in black because you want about 10 seconds times.
Uh-huh. Yeah, that's just something you need to know, that the time to fully charge or discharge is 10 times the time constant. I think y'all do know that, right? Yeah. All right. That's going to be one of your free response. I might also ask you, since it's a free response, I might ask you to do a couple of things. I might ask you to tell me the time constant along en route to the answer. you have to find it anyway. And I might ask you to draw this function for that. But if it's a decay function, it looks like that. If it's a growth function, which is this 1 minus e, the 1 minus e, the growth function looks like this. Qt. This is the growth function. No, that's not right. All right, I shut down about 10 o'clock. What is the growth function? Looks like this. Oops. That's right, huh? Yes, that is right. Okay. I could do that on the free response with a little bit of heads up. I'll try to let y'all know tomorrow at least what a couple of the questions are, but I've already told you this is going to be one, and then the other probably about the thing turning next to a wire. And I might ask you actually, what is the current in the wire? In which case you'd need to know the radius of the turn. It's something that we've done before, but not in that context. So don't worry, it's not that hard. You just need to review it a little bit and be prepared. Alrighty, what else do you want to look at? Want to look at more right-hand rule, or you want to anything in particular?
So we're doing another chapter.
Yeah, you want to preview that just a bit? We're going to see it tomorrow. It's easy, man. It's going to be like nothing. There are really just two things you got to know. Reflection and refraction. It's a short chapter. We'll probably spend 2 days, maybe, not even 2 days on it. Reflection is just that if I have a ray of light that comes onto a reflective surface, it is going to bounce off of that surface such that the incident angle, theta I, is equal to the reflected angle, theta R. So theta I is the incident angle, and theta R is the reflected angle. I think y'all have done this in lab where you had the mirrors. You did the, yeah. So you have the reflection, and usually I have a question that looks like this, where I give you two mirrors that are at an angle. Let's say that their angle is 30 degrees, and then I send in a light ray at a certain angle. Let's say, I don't know, 20 degrees. And I want to know at what angle does it bounce off of the second mirror. So I can draw this. It would go like this, and then it would go like this. And I want to know, what is this angle? Well, I know from the law of reflection, which says that theta I is equal to theta R, that if this angle is 20, then this angle is also 20. And if that angle is 20, this angle is what? Not 180 minus 20, 90 minus 20. So that's 70. And if that angle is 70, what is this angle? Well, that's a triangle. Triangles have what? 180 degrees. That's 80 degrees. Because it's 180 minus 70 plus 30. 80 degrees. And so this angle right here, that little bitty angle, is going to be 90 minus 80, which is 10 degrees. And so this last angle is 10 degrees. Geometric optics is really a lot about triangles and knowing your angles. So this just sort of getting us ready for that. Triangles have 180 degrees, perpendicular lines have 90 degrees, and parallel lines have 180 degrees. So you need to know that. You know that. You just need to remember it. And the other thing is refraction. And in refraction, what happens is I have a light ray that enters into a medium. So let's say I have air on this side and glass on this side. So the light ray enters into the medium, and what it does is it slows down. So the speed of light on this side is 3 times 10 to the 8th meters per second. We call this, by the way, c. That's the variable that we use. So c is equal to the speed of light in a vacuum or in air. It's basically the same. But when it enters into the glass, it's like a truck going into a muddy field. It's going to start slowing down just because it's like trying to slug through all that glass. And over here, the speed of light is equal to 1 point. What is it for glass? No, it's not. It's not 1.5. It's 2 times 10 to the 8th. So 2 times 10 to the 8th meters per second. Is that right? Yes, that's right. So 2 times 10 to the 8th. And we describe this based on the index of refraction. N is the index of refraction. It describes the relationship between C and V. So for example, for glass, C is equal to 3 times 10 to the 8th meters per second. And when the light actually goes into the glass, it's 2 times 10 to the 8th meters per second. So it slows down quite a bit. These cancel, and that leaves me with 1.5. So N is equal to 1.5. There are no units on it. Anyway, the index of refraction tells us how much it slows down. So far you have 2 questions, or several questions, having to do with the law of refraction, and then also the refraction, that when light enters into a medium, it slows down. Now this gets kind of wonky when you have light that enters into a medium at an angle, and y'all did this in lab too. When I have light that enters into a medium, I'll say that this is air and glass, where N is equal to 1.5, and here N is equal to 1, because in air, light travels at 3 times 10 to the 8th. And so 3 times 10 to the 8th divided by 3 times 10 to the 8th is equal to 1. When that happens, the light will bend. And I like to imagine like I have an army of soldiers or a marching band or something, and then they come into this muddy field. This side is going to go slow, and this side is going to go fast. And you know what happens when that happens? When the one side goes faster than the other, right? It's like a tank. You driven a tank before? You have? No? Are you driven like a bulldozer? Lawnmower? Yeah, like those zero-turn lawnmowers, they do that. Although with the zero-turn lawnmowers, like you have one wheel going this way and one wheel going the opposite way, so they need to turn even sharper. But if you just slow down, what it does is it causes this thing to swing around. And so the light ray will swing around too, and it'll bend like that. And so this is theta 2. And the law of refraction, or Snell's law, describes those relationships. It's really just a geometric argument. It's not really physics at all, but it's based on that index of refraction, on how the velocity slows down. This is also called Snell's law. I think there's a question on your OpenStax quiz about what is Snell's law. It's just the law of refraction. And that says that N1 sine theta 1 equals N2 sine theta 2. And so if I know theta 1, for example, if theta 1 was equal to 30 degrees, I can figure out theta 2. Hey, this would be a good free response question. I could ask you to calculate theta 2 and then also to draw the diagram. So I would have 1 sine of 30 equals 1.5 sine of theta 2. And then it's just solving for that. I get 19. Yeah, what y'all got? It's okay. I'm pretty sure it's right. So 19 degrees. It makes sense because I know that theta 2 from how I've drawn my diagram should be less than 30 degrees. Okay? Yeah, let's do that as free response number 3. And maybe the fourth free response, it'll just be like a gimme, like who's my favorite student kind of question. No, we're not going to do that. In fact, y'all don't even get those anymore. See, I got you. Okay? We're about to wrap up anyway here. All right. Any other questions, y'all? All right. Listen, let's stop there. But I'm around. I'm not leaving until 4:30. But I have a meeting in about 20 minutes.